So every biochemical reaction needs energy. Either it takes in energy or it releases energy. Okay. So whenever a biochemical reaction takes place which requires energy, for example in glycolysis, when glucose gets converted to glucose 6 phosphate, it requires energy, and these energies are derived from high energy phosphates. They are derived from high energy phosphates. For example, the most famous one which you know is ATP. ATP hydrolyzes into ADP plus PI and releases something like 7.31 kilocalories of energy. So the high energy, actually the energy is stored in the bonds. The energy is stored in the phosphate bonds. And like here, what it's written, high energy phosphates have a value which is greater than that of ATP. So these have ATP and greater, they are high energy bonds. That of ATP can talk ATP hydrolysis. Okay, and the bonds in the high energy compounds are referred to as high energy bonds, and they are represented by a squiggle. The squiggle is this sign. So basically, Lippmann was the first person who classified this particular high energy bonds and their importance. Please. So high energy phosphates basically are pyrophosphates, ATP, ADP, not ADI, ADP is also GTP, CTP, TTP, DATP, DTTP, DCTP. You have acyl phosphates, 1,3-bis-phosphoglycerates. This is a intermediate of glycolysis. Glycolysis intermediate. Then you have enol phosphates, also an intermediate phosphoenol pyruvate. It is also an intermediate of glycolysis. So if you read glycolysis perfectly, completely, totally, basically you will get knowledge about everything. So in my opinion, that is the most important biochemical reaction which you can study. Okay, that is the most important one which you can study. You can study Krebs cycle, you can study others are basically to understand how a biochemical reaction takes place. Glycolysis has got most of the examples. For example, ATP, ADP, you have a phosphate transfer, you have kinase, phosphatase, and you also have isomerases working. You also have NADPH. You have all these things, so you can understand the mechanism of high energy compounds like this. Then you have the thiol esters. They are acyl and acetyl compounds. It's also in the acyl compounds. Basically, you will find them in fatty acid, fatty acyl CoA. Over there is an ATP hydrolysis takes place. Beta oxidation, you can find them. Then you have the guanidophosphates, phosphocreatinine. In muscles, ATP depletes, so this phosphocreatinine from the muscles, it breaks. The phosphate is taken, the energy is taken, and too much exercise, you have accumulation of creatinine in the blood. If your kidneys don't work properly, this creatinine level will go up. So even if you are exercising hard, your creatinine level rises. But your kidney, if it's working fine, it removes it. Huh? If you take additional creatinine, it will increase. There are creatinine supplements. Where those who do physical in gym, I see when I go to the gym, I see many young boys inside. They have these creatinine supplements kept, whey proteins, creatinines. They keep it in the lockers. For me, in my at my age, it's more like to keep myself fit. But for young people, those who want to make muscles, they really do weight training. For me, the weight training is light weight training. Although I can increase it, but some exercise they told me don't do it. Normally biceps or if you do back exercises, that's fine. But creatinine is released. As long as kidney is working fine, you can do weight training. If your kidney has a problem, kindly don't do weight training. Even though I am diabetic, I am supposed not to do weight training. I am not supposed to do weight training, but still, since my kidney is working fine as tested, I can do weight training, provided I keep my sugar under control. So let us go to the first, ATP. So ATP is the chemical link between catabolism and anabolism. So catabolism and anabolism, it is a chemical link. Anything which breaks down, ATP gives energy. Anything which joins and releases energy, ATP can take back that energy somehow. It is the energy currency of the living cell. It is basically a nucleotide. Rather, you can call it a ribonucleotide. It's a ribonucleotide. RNA is nucleotide. N2 base, the nitrogenous base is adenine, a pentose sugar ribose is present, and a triphosphate unit is present. Okay. Triphosphate unit is present. Then the role of ATP as an energy carrier, you have to concentrate on the triphosphate which is present. PPP, triphosphate bond which is present. It is an energy rich molecule because of its triphosphate units, and it contains two phosphoanhydride bonds. We will see what a phosphoanhydride bond is. So the next page, go to the photo drawn by Uma. The picture drawn by Uma, not a photo, it's the sketch. Very nicely drawn. On the top right, you can see NH2N, that is the nitrogenous base adenine. That is attached to the ribose sugar. Okay. And that is attached to CH2. Normally, when that phosphate is not attached, over there you have CH2OH. But when phosphate is attached, CH2O, P, bottom double O, double bond O, single bond O, you have a negative charge, O minus. Then O, then comes the high energy pyrophosphate as a squiggle. It's given as a squiggle. The first O is the alpha bond. Then you have the beta. And the third one is the gamma. Alpha, beta, gamma phosphate. So these are the phosphate units. PPI, it's a pyrophosphate. Whenever you say PPI, it's basically the two phosphates, the beta and gamma phosphates coming out with release of 7.31 kilocalories. Per mole of the compound. So when ATP is hydrolyzed, 7.3 kilocalories of mole is released, therefore minus sign. It's the Gibbs free energy. Gibbs free energy means it negative means it releases energy. Then you have ADP, when it's broken to ADP. Again, when ADP is broken to adenosine, AMP, you have 7.3 kilocalories. When it is broken, AMP is broken into adenosine, you get 3.4 kilocalories per mole. So it's a highly energy rich compound. So a large free energy delta G0 is liberated when ATP is hydrolyzed to ADP and PI, orthophosphate. And PPI is pyrophosphate. Single high phosphate is orthophosphate, and this is PPI. You can check hydrolysis means water breaks it, so ATP plus H2O, ADP plus PPI, and you have minus 7.3 released. Again, when ATP plus H2O is again hydrolyzed in another word, it happens in beta oxidation. Basically, it releases almost like 2 ATPs, but not 2, so it's something like minus 10.9 kilocalories per mole is released when it forms AMP plus PPI. Bolo, no question? In beta oxidation, this particular AMP plus PPI is formed. First step. So among the next page, among all phosphate containing molecules, ATP has got a central location. Compounds with delta G more than minus 7 kcal per mole or minus 30 kilojoules per mole, that's a conversion, they are regarded as high energy compounds. So it should be more than ATP or more. So she has given hydrolysis of some phosphate, high energy phosphate compounds. The figure, look at the figure. Phosphocreatinine somewhere between minus 12.5 and 10. This phosphoglycerate, it's got two phosphates. So at around 12.5 energy is released. Phosphoenol pyruvate something like minus 15. And lower energy is glucose 6 phosphate. You don't call it high energy. Okay. This is a wonderful table she has compiled. She has chosen actually. So the standard free energy change, it's the measure of the difference in the free energy content of the reactants and products. So like I told in the last class, all the substrate and the product, they have got some internal energy, that is the Gibbs free energy. And when a substrate with a higher energy goes to a product with a lower energy, energy is released, and that is the Gibbs free energy change, delta G degree. Then there are four important factors. One is known as resonance stabilization, electrostatic repulsion, increase in entropy, and stabilization due to hydration. So, how this reaction takes place? These are the things which takes place in ATP hydrolysis. So you see the picture C. There is a water molecule with 2 electrons. It targets the first phosphate. Result is the electron pair, it shifts to the oxygen. Okay. And this is basically ATP 4 minus. 4 negative charges. You can count 4 negative charges. Can you count 4 negative charges? So now hydrolysis takes place with relief of charge repulsion. So many negative charges are present over there. So what? Negative charges that repel each other, right? They repel each other. Positive charges repel each other. So this molecule is just waiting to be broken. Moment 2 electron comes, attach, breaks open. Okay, and then you can see before resonance stabilization that orthophosphate molecule which has been formed, the PI molecule, it is stabilized by resonance. Resonance means The electron pair in the double bond, it moves to migrates to another bond, leaving a minus charge, keeps on migrating back and forth, resonance. The result is that moment there is the stability is because since the double bond is moving from here and there, so at no point you will find that this place is vulnerable. Although there is a gap where the molecule hits and hydrolyzes, so this molecule is made stabilized. এখানে ভাঙতে গেলেই দেখলো আবার একটা ইলেকট্রন বন্ড এসে গেল, ডাবল বন্ড হয়ে গেল, ডাবল বন্ড থেকে ভাঙাটা কঠিন. So in the next photo you can see all the double bond has moved away and all the four are become delta minus in that orthophosphate. This is resonance which is taking place in the phosphate. Then ionization which is taking place. In the end of the in this ADP2 minus, you see an OH at the end. O is not left as O minus. When ionization takes place, this H plus goes out and it becomes O minus, so that becomes negative. H joins and leaves. So this is ionization which takes place. So other compounds, the next page, which have large free energies of hydrolysis, you look at phosphoenol pyruvate, the structure of phosphoenol pyruvate. CH2 double bond C, on the left side you have an O minus, then a double bond, and you have the high energy phosphate. Water comes in, hydrolysis takes place, inorganic orthophosphate comes out. And look at that compound. And here at this stage, energy is released. Then tautomerization takes place from the enol form to the keto form. Phosphoenol. So CCH2, this is the enol form. C double bond CH2 enol form. And then you go to the keto form, COCH3. That H from the OH has come and attached, it becomes CH3 and it has become a single bond. So this goes enol to keto, it's like shifts, it's reversible. Keeps on going till equilibrium is reached. So phosphoenol, so like minus 61.9 kilojoules per mole, it's not kilocals. সেই সময় অ্যাটাক করলেই উইক, তারই মধ্যে ঢুকে অ্যাটাকটা করে দিল, কিন্তু সাধারণত মানে খালি এদিক ওদিক করছে, মানে ইটস হ্যাপনিং ইন মিলিসেকেন্ডস. It's almost like at that moment 10 molecules are in the keto form and 10 molecules are in the enol form. So when 10 molecules shift to keto form, 10 molecules are shifting to enol form at the same time. So it's stabilized at no point, but 10 molecules of them are then vulnerable for attack of hydrolysis. Something like that, imagine, but it goes, you are visualizing this as a single hit reaction, but it's more like a probability of where the electron sites. Electron is like a cloud. Where the density of the cloud is more, the probability of finding that electron is highest there. You cannot predict the momentum and the position at the same time of an electron. Heisenberg's principle. At the same time, so it's the moment you say, oh, ekhane ache, you don't know where his position is. You're saying the position, you don't know what the energy is, something like that. And if you don't know the energy, you cannot define the electron, whether it's a high energy electron or low energy electron. But I'm sort of positioning it, making it into a position and momentum together, just to visualize, but it doesn't take place like this. So this is hydrolysis of phosphoenol pyruvate. Then you have phosphocreatinine in muscles. You can see the phosphate, she has kept it in blue, and the creatinine, she has kept it in black. Hydrolysis takes place, this phosphate goes out, orthophosphate goes out, PI, and you get the creatinine molecule which is present. This is stabilized by, this creatinine is stabilized by resonance. As you can see that whenever this double bond that is taking place, it's becoming single bond and double bond, single bond and double bond. So creatinine becomes a stable molecule. And you have minus 43 kilojoules, it's not kilocalories, okay, released. So this is hydrolysis of phosphocreatinine. Then she has given a list of standard free energies of hydrolysis of some phosphorylated compounds. Phosphoenol pyruvate, this is kilocalories, not kilojoules. Minus 14, 11.8, 1,3 bisphosphoglycerate, phosphocreatinine, minus 10.3, ADP, minus 7.8, ATP hydrolysis, minus 7.3, ATP to AMP PPI, minus 10.9. Just keep in mind about all these things. 1 mark questions. AMP minus 3.4, so and so forth. But anything below ATP is not high energy compounds. Okay, so this is enough for your studies. For your exam, this is enough. You can read Orgo's note also. That's all. The example দিয়েছে, example double bond migrate করছে study, because creatinine is a very important molecule. You can use benzene also as an example of stabilization. Anywhere there is a double bond, big compound which is double bond with single bond, that it always migrates. Electron একবার এখানে আসছে, so you cannot say the position is over here, you cannot say whether the position is somewhere else. It's always like this. You can use any example for resonance stabilization, but basically here in this creatinine is stable because of this resonance stabilization. Phosphocreatinine is not that, it's waiting for some water to kill it, to break it, to release energy. যত energy, the less stable. More energy, less stable. ঠিক আছে?